In this course, we will study data analysis. It's to discover hidden patterns in the data, or to find underlying processes behind the observations. This is a very broad premise. There are patterns in data. The patterns are discoverable. The patterns are useful in future tasks. There are many practical applications of data analysis. For example, to analyze bank transaction records to find dubious behaviors such as money laundering or tax avoiding, to analyze the gene sequence of a patient to predict if the patient is at risk of certain diseases, or to analyze image data to make critical decisions in tasks such as automatic driving. Those applications are the same premise of data analysis, that hidden pattern behind the data put into different contexts and application areas. Various techniques and mathematics skills, the algorithms have been developed to solve those problems. Those techniques are called by different names as different disciplines in the literature, such as machine learning, statistics, artificial intelligence, decision theory, information theory, etc. But at the core, the essential goal is to find hidden patterns in data. So, for each task, the desired product are the patterns. However, in this course, we will head for a more comfortable world. You can sit there, let the computer have a look at the data, analyze the data automatically for you, and at last handle you a set of patterns which appropriately interpret the data. We will study a few simple but highly effective and widely applied and successful methods to teach the computer to discover patterns from examples. Perhaps the proper way of studying how to learn from examples is by seeing an example of learning from examples. Let's say we want to examine if there is any connections between the amount of time a student spends on some subject and the final score the student may get. Let us first make a picture of this problem. If we make the horizontal line as the number of hours a student spent on some subject, and the vertical line as a score, so our historical data of hours spent versus final scores can be drawn like a two-dimensional point on the plan. For example, if you look at this guy, this is the amount of hours he or she spent on the subject, and here is the score. The task of analysis is to see, is there any pattern in the data, in the historical data of student performance versus student's effort? And if yes, I give you some certain amount of hours spent a week and let you predict what is the likely result of this student. If we consider it carefully, setting up the task makes a fundamental distinction between the two aspects of the data. One is the number of hours. Here, this quantity is and will always be available in the problem. It is available in the historical data, of course. And when the analysis has been done and facing a student it has unseen, it is also available, either by observation. For example, if one of your classmates comes to you and asks you to predict the score, you then ask him or her, could you tell me, please, how many hours you spend on the subject? If you can get this answer, okay, we are in business. You can make a prediction. Otherwise, the system is not work for your classmate. And on the other hand, you may directly control this quantity yourself. If you view it as a variable, you can determine the value of this variable. For example, you are a very busy person. You would like to spend only a certain amount of time, or you has to limit your time on this subject. You may want to know how likely you can get a reasonable result with some reasonable chance. On the other hand, the scores, they are available in the historical data, but they are unavailable when the system is put into use. Otherwise, there is no point to do any analysis and make predictions. We call these quantities that are always available observations and give it a symbol x. We call these quantities that is only available in the historical data and are the unknown target of predictions. We call them, of course, targets and give them a symbol y. So the central problem of data analysis is to discover patterns that allow us to form map from the domain of the observation to that of the target. We call it target function from x to y, and the target function is unknown. Let's look at the elements in our problem of approximating the target function. First, we have a set of samples that are generated from the target function. These are our data. Second, less obviously, although there is no limit on how you can approach the target function, but it does no harm to conceive all the possibilities of your candidate patterns and make it explicit in our mind map of the framework of analysis. We call it H. H for hypothesis, which is the fancy way of calling pet theories or the patterns behind the data. For example, you would like to consider all linear relationships between the scores and the hours. Then each of the hypotheses is a linear relationship and can be represented by a line on the combined domain of the observation and the target, or of course this plane, like this. Okay, perhaps this guy corresponds to here and this guy corresponds to here. The next step is to have an algorithm that searches the hypothesis space and find the best match of the data. The match between the data and the hypothesis is according to some criteria. Sometimes the criteria is implicitly integrated in the searching algorithm, and sometimes it is explicitly defined. For example, in our case, or find a linear hypothesis that match the data in the student performance versus the hours spent. One can use the Euclidean distance in the 2D space like this, or alternatively, one can concentrate on a certain number of hours spent by the student and measure the prediction error of a hypothesis given for a certain number of hours, like this. Anyway, given the criteria, the searching algorithm gives out a final hypothesis it found as the underlying pattern of the data. That is the result of data analysis, and we will use that for future predictions. So here we draw a diagram of the mechanism of data analysis from a very basic example. This framework applies to a very broad range of analytic questions. In our study, we will take a closer view of all these aspects. The data. Most practical data needs some sort of processing before they can be useful in data analysis. There may be various issues. Some attributes may not be available in all examples in the data, that is called missing data, or some attributes may not be convenient for mathematical treatment. For example, if your data contains a categorical value like a user gives A, B, C rankings to some product, these rankings cannot be included in mathematical computation before we find some way to quantize them into numerical values. Such skills and tricks are normally named as data massage. As the name suggests that it is more like an art than a science. It is very difficult to summarize all those data pre-processing skills in a systematical way. We will encounter some of them in our demo examples and in your lab exercises, and you may discover some of them by yourself or by trial and error. But one thing to be certain is that your skill of dealing with data will improve with your experience of dealing with data. From a technical point of view, the heart of the analysis problem is to choose the hypothesis set and the searching algorithm. These two parts combined are called the data model, which is the focus of our study. And when you look into a technical proposal of solving an analytic problem, or you read a paper, these parts are the beef that should draw your attention. As we mentioned before, in this course, we will study some basic and important data models. But moreover, we will also study the problem from the other line of the story, which may help to answer such potential questions. Why these algorithms? Why all those algorithms? Isn't there a magic bullet to solve all the problems? When and in what circumstances to apply a certain algorithm to a particular problem? When given some problem that we have not learned in the course by your boss or your customer, how to combine those methods we have learned or to make extensions to solve the new problem? Maybe that is the most important question. The other line of the story answering those questions, start by asking a fundamental and intriguing question: why analysis is possible at all? Remember that in our basic premises of analysis, the target function is unknown. By unknown, we mean really unknown. This is a murky area that will never be clarified and will never be realized. The only way you can look into this area, or your learning algorithm to peek into this area, is through the data. So, isn't it possible that someone is playing a really bad joke on you, and the trend of the data should be like this, and the data samples are chosen to deliberately deceive you, so that at last you end up with a non-existing pattern, or we can say a particular poor hypothesis, which is useless for making any further future predictions. The short answer is very sad. There is no guarantee against such very unfortunate situation. So, is analysis doomed? Should we stop here? Of course not. The good news is that although it is possible that learning goes wrong and very wrong, but it is extremely unlikely to go wrong as long as your data model is not too deceivable. Or put it another way, your data model is not trying too hard to discover its imaginary patterns in the data. Of course, one must be specific about the meaning of extremely unlikely, and when the data model is trying too hard. There are several intriguing views on this famously called generalization problem. One school of thinking follows this learning framework naturally. It starts with a binary classification problem, where the targets are 0 or 1 predictions. Given a certain hypothesis, the entire domain of X is categorized based on whether the hypothesis agrees with the target function. Here we can imagine a bin of marbles, in which the red marbles represent that H and the target function f are different, and the green marble means they are the same. Or we can say H agrees with the target function on that particular sample X. And the distinction based on whether H agrees with F on the data samples applies also on the observed data set. That is to say, we can color each of the observed sample green or red based on whether H agrees on F. Obviously, we want our H agrees with F as much as possible. Ideally, it agrees with F completely and we have the true target value. So let us call the agreement between H and F the performance of H. The theory goes like that. The more data you have, the more accurate you can estimate the performance of H based on your data. When your data consists of many samples, and then if you have a hypothesis which performs well on those many examples, then you can handle out this hypothesis with confidence that it will be good when facing the data that you haven't seen so far. So far, so good. But your confidence is associated with a particular hypothesis. If you have many hypotheses to play with, you may run out of luck. You may finally find a hypothesis. You think the performance is good based on the measurement on the observed data, but actually the estimation is very inaccurate and the out-of-sample performance is very bad. So the capability of generalization is the central protagonist in any story told from data. The basic data models we will study, they employ different techniques to have a good trade-off between find a good hypothesis so that it performs well in the observed data samples and ensuring that the generalization is good. Or informally, as we have said before, they try to find good hypotheses, but they do not try too hard.